Why do satellites not just tumble in space like a loose wrench? And how can they aim a camera or antenna at one spot for hours without constantly firing rockets? The short answer: satellites stay oriented by swapping angular momentum with spinning flywheels called reaction wheels. Spin a wheel faster one way, and the satellite rotates the other way, like sitting on a swivel chair and twisting a bicycle wheel. In space, which way you're pointing is called attitude. And it's not just left-right. It's 3 rotations: roll, pitch, and yaw. A satellite might need to keep solar panels facing the sun, an antenna facing Earth, and a camera pointing at a tiny target, all while it's moving at thousands of kilometers per hour. Here's the trick: angular momentum is conserved. If nothing external pushes on the spacecraft, the total spin amount has to stay the same. So when a motor speeds up the wheel gains angular momentum. To keep the total balanced, the satellite body gains angular momentum in the opposite direction, meaning it rotates. Slow the wheel down, and the spacecraft rotates the other way. No flames, no propellant, just internal momentum trading. One wheel can only rotate you around one axis. Real satellites use 3 wheels for 3-axis control. Often there's a 4th wheel angled off-axis because space is unforgiving and redundancy is cheaper than losing a mission. With 3 wheels, the satellite can smoothly point anywhere, making tiny corrections that look almost magical from the outside. Reaction wheels aren't guessing. A satellite runs a constant feedback loop. Sensors estimate attitude, gyros feel rotation rates, sun sensors know where the sun is, and star trackers compare star patterns to a catalog. Then the onboard computer calculates the error, how far off you are, and commands each wheel to speed up or slow down just enough to cancel that error. This happens continuously, making pointing stable enough for high-resolution imaging and tight communication beams. But space isn't perfectly quiet. Small external torques constantly push on a satellite, some like pressure on panels, thin atmospheric drag in low orbit, magnetic effects, and even gravity gradients. Reaction wheels fight these, but there's a catch: the wheels have speed limits. If a wheel keeps spinning faster to counter tiny pushes, eventually it hits its maximum. That's called wheel saturation, and at that point, you're running out of control authority. So how do you reset? You dump momentum, you push against something external to bleed off the stored angular momentum in the wheels. Many satellites use Magnetorquers, electromagnetic rods that interact with Earth's magnetic field to create a torque. It's like a spacecraft-sized compass you can electronically lean against the planet's field. Some missions also use brief thruster pulses for unloading. The goal is simple: bring wheel speeds back to a comfortable range so the wheels can keep doing fine pointing control. Reaction wheels are amazing, but not perfect. Spinning hardware can create tiny vibrations that blur ultra-sensitive instruments. Bearings wear. Electronics can fail. That's why satellites have fallback behaviors like safe mode, stabilize, point solar panels toward the sun, keep power alive, and wait for commands. And it's why designers often add extra wheels, Magnetorquers, and fault detection logic. In orbit, you don't get a second chance to tighten a bolt. So satellites don't stay steady because space is calm. They stay steady because they're constantly correcting, trading angular momentum with reaction wheels, and occasionally dumping that momentum back to the environment. Now your turn. What should we break down next? How star trackers recognize constellations, or how GPS satellites stay synchronized in time?